Hello everyone. So this is a nice problem from mechanics. Let's read through the problem once. There is a hemisphere of mass capital M and radius capital R which rests on a smooth horizontal table. Friction is not there. A vertical rod of mass small m is held between two smooth guide walls supported on the sphere as shown. There is no friction between the rod and the sphere as well. A horizontal string tied to the sphere keeps the system at rest. So the entire system is initially at rest. So there are two parts to the problem. In the first part, we have to find the tension in the string, and in the second part, if the string is cut, we have to find the acceleration of the hemisphere immediately after the cut. So for solving the first part of the problem, let us draw the free body diagram of the sphere and the rod. So I have the diagrams. So let us say this is the sphere and this is a rod. So on the sphere, the forces acting are a normal reaction by the ground. Let us call this as R. Weight of the hemisphere, capital Mg. There will be a contact force between the rod and the hemisphere. So a normal reaction will act on the hemisphere like this, and due to the string, a tension T will act to the right. For the rod, there will be a normal reaction by the guide walls N prime in the horizontal direction, and there will be a normal contact force due to the hemisphere in this direction at an angle theta with the horizontal. So since equilibrium is there, so for the hemisphere, we can write the equilibrium equation in two directions, vertical direction and horizontal direction. So for vertical direction, I can write R equal to mg plus, and there will be a component of n in the vertically downward direction and a component of n in in horizontal direction. So vertical component of n will be n sin theta. So mg plus n sin theta. In the horizontal direction, T will be balanced by n cos theta. So for the horizontal equilibrium, we can write T equal to n cos theta. Next, for the rod, again there are equilibrium in horizontal and vertical directions. So in the horizontal direction, we can write n prime equal to n cos theta, and weight mg will act in the downward direction, which will be balanced by n sin theta. So n sin theta will balance the weight of the rod. Let us say this is equation 1, this is equation 2, this is our third equation, and this is our fourth equation. Since we have to find the string tension, capital T, that is from equation 2, but we need the value of capital N. So capital N we can substitute from equation 4 in equation 2. So N we can get from here, small mg by sin theta. So from 2 and 4, on solving, we directly get the value of T as mg by sin theta, and into a cos theta is there, which will give us mg cot theta. So this is the answer to first part. For the second part, we have to find the acceleration of the hemisphere after the string is cut. Once the string is cut, there will be no more equilibrium. So the system, the hemisphere will start sliding towards left, and the rod will start slipping in the vertically downward direction. So let us see the free body diagram of the hemisphere. The forces acting on the hemisphere are as usual, but this time acceleration will come into picture. So if we call this distance as x and this distance as y, then one thing is sure, with time x will increase and y will decrease. But this relation x square plus y square equal to r square will be valid at all the time. If we differentiate this equation, we get 2x into dx by dt plus 2y into dy by dt equal to 0. 2 gets cancelled, and if we transfer y dy by dt on the right, we get x into dx by dt equal to minus of y into dy by dt. So we can say that dx by dt is the velocity of the hemisphere in the horizontal direction towards left, and dy by dt is the velocity of the rod in the vertically downward direction. Minus sign just indicates that these velocities minus sign indicates that if x is increasing, then y is decreasing. So if we go by magnitudes only and differentiate further, then on the left hand side we get dx by dt into dx by dt and plus x into d2x by dt square, and we are now going to ignore y, we are now going to ignore the minus sign, and if we differentiate the term on the right hand side, we get dy by dt into dy by dt and plus y into d2y upon dt square. Now initially when the motion starts at t equal to 0 plus, both these velocities will be almost equal to 0. So we can say that at t equal to 0 plus dy by dt as well as dx by dt, both will be equal to 0. So from this boundary condition, we can say that x into d2x by dt square will be equal to y into d2y by dt square, and d2x by dt square is nothing but the acceleration of the hemisphere in the leftward direction into x equal to y into d2y upon dt square is the vertical acceleration of the rod. So acceleration in the vertical direction of the rod. So from here we can write ay equal to x upon y into acceleration of the hemisphere. X upon y we can write from the above diagram. X upon y is nothing but cot theta. So we get the constraint relation ay equal to ax into cot theta. Now coming back to the problem, we have to calculate the acceleration of the hemisphere immediately after the string is cut. So now again we have to use the free body diagram, and then we have to introduce the acceleration. So for the hemisphere, the acceleration towards left is caused by n cos theta, by the difference of n cos theta. The tension is no more there, so only n cos theta will be responsible for the acceleration of the hemisphere in the leftward direction. And for the rod, since now it is accelerating in the downward direction, so from this free body diagram we can say that mg and the difference of n sin theta will cause the acceleration in the vertically downward direction. So for the hemisphere, we can write that n cos theta will cause m into ax, and for rod we can say that small mg minus n sin theta will result in small m into ay. So if we solve these three equations, we have to get the value of ax. So we need to eliminate n and ax. So on solving, I have the answer with me. We will get the value of ax, which is the acceleration of the hemisphere, as equal to mg upon capital M tan theta plus small m into cot theta. So this is the answer to the second part of the problem. Hope you get it. So you can go through the solution once. This is a very nice problem from Newton's laws of motion. Thank you very much.